Okay, so we've defined what a random variable is, and now remember in our definition of random variable, um the important aspect of that definition is that there's an underlying probability space that's governing the process, the random process, but we're actually going to measure certain quantities out of the results of that process. And that's what gives us rise to what's called a probability mass function. So the probability mass function are the probabilities that get assigned or that are implied or induced on the values of the random variable as a consequence of two things. One is the underlying probability measure on the probability space, and the other is the definition of the random variable of the function. Okay, so let's suppose we have X. So we have a probability space, omega, set of events P, and the set of events is just going to be, for our sake, the set of all subsets of omega for right now, but this is a probability space. This determines the process, right? The tosses of the coin or the rolls of the dice, etc. And we have a random variable X on that space. So if the process governing the outcomes up here is governed by P, then since that governs the inputs to our function, that's going to tell us something about the outputs of the random variable, right? So let's write that down. So P governs the behavior. So governs the behavior or describes the behavior of describes the random behavior, just generally speaking, the behavior of outcomes in omega, and therefore describes the inputs, describes how the input to the random variable X behave, and that in turn determines the behavior of the output, which is the realization of the random variable X of omega. And how this all comes to fruition is through what's called the probability mass function, sometimes abbreviated as PMF, is that we can define, so given the above ingredients, we're going to define a function on the range of X to 0, 1. The idea is that the P of X, I write it as P lowercase capital X, that's to index it by the random variable. And we define it in such a way so that P sub big X of little x is equal to, this is the probability, sometimes also written, the probability that the random variable assumes the value little x. What does that mean, technically speaking? It's because P, remember, P is the probability distribution on subsets of omega. So really, it's a function on subsets of omega. So it has to be defined on subsets of omega. And here's what that subset is. It's the subset of omega such that the output of the random variable equals a specific quantity, which is defined as the sum over all omega values for which x omega is equal to a specific quantity of that singleton subset. Okay. Now this is, I think at first glance, seems a little bit notationally heavy and probably a bit more complex than we would like it to be. And that's where it's worthwhile to go into some examples to really illustrate how this comes to light in practice. There's something that's pretty straightforward once we see how it works, but we need to see some examples to see what this definition actually means, and that's what we're going to talk about next.